Welcome to the course Introduction to Probability Theory and Statistics. In this topic, we are going to discuss about testing of hypothesis. We have already covered two modules or two topics of statistics part. The first one was descriptive statistics and sampling distributions, and the second topic was estimation. Both point estimation and interval estimation was discussed. This is the third topic, that is topic number 11, testing of hypothesis or hypothesis testing. Since the course is a very elementary nature or introductory nature, my interest is to discuss what is the meaning of null and alternative hypothesis, Neyman-Pearson theorem, and few hypothesis testing started with the population mean, then population variance, and testing regarding population distribution, and then testing regarding contingency tables, and finally test regarding proportions. And finally, we are going to discuss testing regarding one particular type, that is a name called analysis of variance. That is also basically testing regarding different population means. So, therefore, there is a very particular name called analysis of variance. In this topic, we are going to discuss about only the very limited theory and a few examples, and how to solve and how to conclude the concepts what we learned it. We won't explain the proof of the theorems which is related to the testing of hypothesis. We will state some of the important results to cope up with the problems which we are going to solve it. Let me start with the topic of testing of hypothesis with some examples. Examination marks follow normal distribution with the mean 15 and variance 3, parametric testing. That is one example. And another example is, most of the time the student president is from Shivalik hostel. Parameter involved is proposition. The average talk time on a telephone by a person which is 3 minutes and follows exponential distribution. Parameter involved is a distribution of population itself. And the fourth example is a traffic speed and the traffic volume are correlated with the correlation coefficient equal to 0.7. Here we are testing if two populations are independent or not. So, these are all the statements regarding the population. The first statement is about the population mean and the population variance. The second one is about the proposition of the population, and the third example is the distribution of the population, and the fourth example is the correlation between two different information that is also sort of related to the population. Whenever you make such a statement, you may have a doubt whether this statement can be accepted or rejected. So, in this topic or in this model, we are going to conclude whether the statement which you made it with respect to the population, either in the form of parameters or in the form of a distribution or some information related to the populations, whether such a statement can be rejected or not to be rejected by getting some sample information. So, there the statistical analysis comes into the picture. suppose you make some statement, then that statement can be rejected or accepted. We usually avoid the statement accepted, not to be rejected, with the given observation. That means with the sample of size n, we are going to conclude whether the statement can be rejected or not to be rejected with the given confidence limit. That means you have to supply the confidence limit, that alpha value or 1 minus alpha 100% confidence, whether the statement which is already made can be rejected or not to be rejected with the given confidence level. So, we always make the confidence level or level of significance as the alpha, equivalently saying 1 minus alpha 100%, you reject the statement or not to be rejected the statement for a given set of sample of size n. So, even though I have listed these 4 examples, in your mind you may have many more examples. Not only the population parameters of mean or variance, you can have many more parameters involved with the population, that also can be made it, or function of parameters. Similarly, the proposition can be of any form. This is a one simple example, whether the example which I have said earlier, the female population, whether they read that particular magazine or not, what proportions the female population prefers that particular magazine. So, that is also proportion problem. And the average talk time, that follows 3 minutes. So, that means you can think of 2 different problems for a given distribution, whether the average talk time is going to be 3 minutes or not, whether that can be acceptable or not to be acceptable, or it can be rejected or not to be rejected, or whether you conclude the population follows exponential distribution or some other distribution. Similarly, the last example, you can think of whenever you take some observation, whether the observation involves many attributes, whether those attributes are any dependency over it or there is no dependency, or if you say that there is a dependency of this much, whether that can be rejected or not to be rejected. So, these are all the things are possible with the testing of hypothesis or hypothesis testing. So, basically the statement which we made with respect to the population, that we call it as the hypothesis or statement, and the statement can be rejected or not to be rejected, that is the test. So, with this brief introduction, we move into the definition. So, before we go to the testing of hypothesis, let me give a little theory, then I will move into the problems. Obviously, we go for making the assumption of distribution to the population. Then those types of test is called a parametric test. There are 2 types of testing of hypothesis. One is a parametric test, other one is non-parametric test. In this course, we are going to concentrate on parametric test. There is a set of test for the non-parametric also. That means we will not assume any distribution to the population. Therefore, there is no parameter involvement. So, we started with the hypothesis testing with the assumption of distribution to the population. That means obviously there is a parameter involvement with each distribution. So, therefore, your small f of x comma theta, that is the probability density function of a population with the parameter theta. There is a possibility theta can be vector also. And the parametric statistical hypothesis is the testing of assertion, that is a statement about the unknown parameter theta with the help of observations obtained from a random sample of size n. So, this is what just now I have made it in a layman language. What is the meaning of a parametric statistical hypothesis or testing of hypothesis with the parametric form. Fine. When you start doing the testing of hypothesis, you should have a statement, and that statement talk about the unknown parameter theta. Always the statement which you want to go for, whether to reject or not to reject, that you keep it as the null hypothesis. The statement which you want to reject or not to reject, that statement you start with the null hypothesis. And the alternative of null hypothesis, that is called the alternate hypothesis. So, this is a very important concept, null and alternate hypothesis, and the hypothesis is going to be called it as a simple hypothesis or composite based on the possible values of theta naught. If it is going to be the single value, then the null hypothesis is going to be called it as a simple hypothesis. If both theta naught and theta 1 consisting of only one point. So, the bigger theta that consists of it could be finite values or countably infinite values, or it could be uncountably many values also, the capital theta. Suppose the capital theta consisting of only two values of theta naught and theta 1, and h naught is theta belonging to theta naught, and h 1 is theta belonging to capital theta minus or other than theta naught, if that is also has only one element. If theta naught and theta 1 has only one element, in that case the hypothesis is going to be called it as a simple hypothesis. Negation of a simple hypothesis is going to be composite. That means if the theta naught and the theta 1 has more than one point, then the conclusion is going to be a composite. We usually study the simple hypothesis in the beginning, and then later we will go for composite hypothesis. So, we usually use the notation h suffix naught. Naught means null hypothesis. H suffix 0 means it is a null hypothesis, that is a starting point, and the complement of null hypothesis, that is a alternate hypothesis. So, based on the statement, based on the possible values of the unknown parameter values of that corresponding population distribution, you will end up, both may be simple statement, one may be simple, other may be a composite, or null hypothesis may be composite and the alternative may be simple, because the alternate hypothesis is a negation of a null hypothesis or complement of a null hypothesis. Fine. So, it is purely depends on possible values of the unknown parameters of the population distribution, that is all. So, there is a possibility, one more information, there is a possibility the null hypothesis may say statement like equal or not equal, less than or equal to, greater than or equal to, and so on. Sorry, not equal. The null hypothesis may most of the time it is equal or less than or equal to or greater than or equal to, and the alternate hypothesis is always, if it is equal then it is non-equal. If it is started null hypothesis greater than or equal to, then it is going to be less than, and similarly null hypothesis is less than or equal to simple, then that is going to be greater than. Fine. So, always we start with the null hypothesis with the equal sign, that is a simplest example, we go for it. Sometimes it is greater than or equal to, sometimes it is less than or equal to also, and obviously the alternate hypothesis is negation of null hypothesis. Now we are coming into next important concept, that is called test statistics and critical region. The approach in which we are going to solve this testing of hypotheses is same as what we have built up the concept with the confidence with the interval estimation. Whatever the concepts which we learned it in the interval estimation, the same concept will be used to conclude the given null hypothesis statement to be rejected or not to be rejected for a given observed data and for a given alpha. That is all. If you recall the interval estimation concept, you are identifying what is the interval in which the unknown parameter can lie with the given alpha by observing a sample size of n. The same concept is used in the testing of hypothesis, whether the statement can be rejected or not to be rejected by considering the corresponding confidence interval, by corresponding interval estimation of the same parameter with the same alpha with the given set of random sample of size n. Fine. And how we are going to do that is the same approach what we have used. 1 minus alpha is the probability which is in the middle part of any statistics which we have designed, and we created alpha probability. If it is a symmetric, keep it alpha by 2, or if it is non-symmetric, you keep it based on identifying the point. So, you identify the interval estimation of a parameter, unknown parameter, by splitting 1 minus alpha probability in the middle and alpha probability in both the tails. Here in the testing of hypothesis, this 1 minus alpha probability, that is going to be the acceptance region, and the remaining acceptance region, if it is a symmetric, you will have a right side critical region of alpha by 2 region, and the left side alpha by 2 of critical region or rejection region. So, if the value of unknown parameter value lies in the acceptance region, then you are going to conclude not to reject the null hypothesis. If the value of unknown parameters for a given alpha for a set of random sample of size n, if it lies within the rejection region or critical region, then we conclude the statement to be rejected. As simple as it is. You do not need to make any confusion about how to start the testing of hypothesis. As long as you have a good knowledge in interval estimation, the same concept is applied along with the statement. Always you start statement with the null hypothesis and prepare alternate hypothesis, and I am going to tell what are all the steps to do that to conclude the hypothesis to be rejected or not to be rejected, that is null hypothesis. Fine. So, that is what we need the statistics first. If you recall, we discussed the statistics in the first module or first topic, and the same statistics concept coming to the picture in the estimation also. Now also we are going to use the same statistics, but this statistics is going to be used is to test the hypothesis, therefore, it is called the test statistics. So, it is a statistics whose value is determined using the realization of the sample. Not only that, this is test statistics, it should involve only the random sample values as well as known parameter values, not the unknown parameter values. if it is involved the unknown parameter inside the statistics as a function of unknown parameters, then it is fine. If it is unknown parameters also inside, then it is not a statistics, because later you are going to evaluate the test statistics, then you are going to do some more steps. So, always this is going to be a function of either purely a random sample of size n, those information. Okay. So, in this topic there are two important jargons, one is called test statistics and the other one is called critical region. The way I explained, the test statistics is a statistics whose value is determined using the realization of the sample, and a critical region which is same as the rejection region as the way I said. That means you are going to reject the null hypothesis if the value of the test statistics, if it is lies within the critical region. There is a theory behind in a simple model we keep f naught of x and f1 of x, which is related to the null hypothesis, the probability density function. By keeping the value of unknown parameter into that particular value, that is going to be the f naught, and if you keep if you make the assumption both are going to be simple, both null hypothesis and alternate hypothesis are simple, then f1 is the probability density function of a population with the parameter value takes the value from the alternate hypothesis. So, in a simplest scenario we discuss both are going to be simple, and later we can extend the concept into simple with composite or composite with the simple, or both are going to be composite also. So, a region is called a critical region if the null hypothesis is going to be rejected, and if it is similarly it is going to be acceptance region, that means your null hypothesis is going to be not to be rejected. The next two very important information which we want to study, that is called error. That is one is called the type 1 error, the other one is called type 2 error. How the error can happen? Basically there are four possibilities can happen based on what is the statement it says and what is the realization. Forget about testing of hypotheses and statistical analysis and everything. Suppose you have a one statement, that statement can be true or false. That statement can be true or false. Similarly, if you have a observed information, that also may conclude the statement can be true or false based on the observed information. That means you have four possibilities. The observed information can conclude true about the null hypothesis, and your null hypothesis also true, that means there is no error in it. Suppose your observed information says false and the null hypothesis is also false, then there is no error in it. The error comes, the observed information conclude which is a negation of the statement which you made, that statement is basically a null hypothesis, then there is a error occurs. Similarly, the observed information says true, whereas the statement is not satisfying or the null hypothesis is false, then also you have error. Therefore, you have two types of error. One is called the type 1 error, that we denoted by alpha, and the second type of error is called the type 2 error. So, alpha is same as integration f naught of x over the omega, and the beta is integration of f naught over the omega complement. So, the question is it is very difficult to minimize both the errors, that is obvious also. It is not easy to minimize both the errors. So, the question is how we can able to fix. It is impossible to objective simultaneously minimizing both types of errors. That is the important observation from the 4 scenarios. Out of 4 scenarios, 2 scenarios are going to be error, and we label it as a type 1 error and type 2 errors, and it is impossible to minimize both the types of errors. So, whatever I said that we have written in the table form. So, how you will end up with the type 1 error and how do you land up with the type 2 error. Now, I am relating the probability of a type 1 error with the probability called alpha. That means you are rejecting H naught given that H naught is true. H naught is a null hypothesis. Given null hypothesis is true, still you are rejecting H naught based on the random sample of size n. That probability is going to be called it as a alpha. That is basically a probability of type 1 error. Whereas the null hypothesis statement is not true or false, given that scenario you are still accepting the null hypothesis statement using a random sample of size n, and that probability is going to be called it as a type 2 error, that is denoted by beta. Fine. And this alpha is same as the level of significance, or the way we discussed 1 minus alpha 100% confidence, that same alpha is used here. So, there is no difference alpha here, the same alpha, that is same as probability of type 1 error. Let us do the simple problem before we go to the testing of hypothesis. Identify or compute what is type 1 error and what is type 2 error. So, the type 1 error is same as the alpha, that you can compute using what I said it in the previous slide, and similarly one can compute the probability of a type 2 error, that beta also. The probability of a type 2 error, after doing all the calculation, it is going to be fx of 28, that value is 0.6068. There is another very important information which you should know, that is called the p value. The way we have discussed many jargons in this course, starting from population, sample, statistics, estimator, of course 3 different distributions, chi-square distribution, student t distribution, F distribution, and so on. This jargon is also, in recently we have discussed type 1 error, type 2 error, alpha, beta. The same way the p value is also important in the testing of hypothesis. I have given the definition of p value. As simple as it is, the smaller the p value, the larger the significance. That is, we reject the null hypothesis if p value is less than alpha. So, most of the statistical analysis they will identify what is the p value instead of given alpha, because the alpha has to be supplied to you, but instead of that most of the time you do not need the alpha business. Instead of identifying the critical region with the given alpha, most of the time we will be looking for what is the p value. So, once you identify the p value, the smaller the p value, the larger the significance. That means we reject the null hypothesis when p value is lesser than alpha. So, this is a connection between alpha with the p value. Of course, I have already explained what is a acceptance region, what is a critical region, and so on. Therefore, the p value is linked with the rejection region or critical region as well as with alpha. This is a very important concept while doing the testing of hypothesis, that is called a Neyman-Pearson lemma. As such, I am not going to discuss in detail about the Neyman-Pearson lemma, because it needs at least 2-3 lectures to explain the theory, to conclude how one can use the Neyman-Pearson lemma to identify or to conclude, reject the null hypothesis or not to reject in a easy problem. That is a big exercise, but still I want you to understand the Neyman-Pearson lemma whenever you want to go for theoretical side or whenever you want to study in depth of testing of hypothesis. Yeah, this is a very important result, that is called Neyman-Pearson lemma, and we start with the null hypothesis against the alternate hypothesis, and both the statements are simple. With that we created the test psi that is going to be a most powerful of its size. As such, I am not going to discuss in detail, but there is a connection between the Neyman-Pearson lemma and the problem which we are going to come across immediately now, that is the testing of hypothesis regarding the population mean. I am going to apply this in a very easy way. So that means we identify what is the critical region for a given alpha. How to identify the critical region, that comes from the Neyman-Pearson lemma. Once you identify the critical region, that is the probability alpha lies in the whole probability density function, then whenever the test statistics values lies within the critical region, the way you created the critical region based on this lemma, then it is easy to conclude the null hypothesis will be rejected or not to be rejected for a given alpha. Now we are coming into the easiest or very first testing of hypothesis regarding the population mean. In this we started with the population follows normal distribution with the mean mu and the variance sigma square. The way we have done the interval estimation for the population mean, the same similar assumptions we are going to take here also, only the population mean is unknown, whereas you know the population variance sigma square. We started with the assumption of population variance is unknown, whereas you do not know the population mean, that is unknown, and the statement is made regarding the population mean, and the population follows a normal distribution with the mean mu and the variance sigma square. The statement is the mu is going to be 8, that is a null hypothesis. Obviously, the alternate hypothesis is a negation of null hypothesis, therefore, mu is not equal to 8. There is no confusion of choosing which is going to be null hypothesis. The way I said, null hypothesis is always either it is equal sign or less than or equal to or greater than or equal to. Therefore, if you say the population mean is going to be this value, that is a statement which you want to test or verify. That means that you have to assign it as a null hypothesis. You have to keep the population mean is going to be so and so value, that is equal sign, that is going to be the null hypothesis. Once the null hypothesis is fixed, alternative is negation is going to be alternate. We are going to test this statement with the level of significance alpha is equal to 0.01. That means the probability 0.01 in the critical region. Since we made a normal distribution as the distribution for the population, and we are working on testing hypothesis regarding the population mean. You have to identify the test statistics, and you will land up the critical region divided into 2 halves, because you will end up with the standard normal distribution as the test statistics. So, the question is whether the statement of population mean is going to be 8 to be rejected or not to be rejected with the given level of significance alpha for a data information. So, here the data information is instead of giving all the 50 data, they have given the sample mean of the 50 data. Why? Because you do not need actual data, you need only the sample mean for this calculation. You need only the sample mean. Therefore, for a data of size 50, the sample mean is provided to you. With that information, with the level of significance alpha is equal to 0.01, whether the statement population mean is going to be 8 to be rejected or not to be rejected. That is the question. Of course, the population variance is also given, because if the population variance is not known, then you have to go for a different approach. Yes, any testing of hypothesis in general of 5 steps. The step 1, you identify the null hypothesis. Once the null hypothesis is identified, you identified the alternate hypothesis. Step 2, related to this problem, you have to identify the test statistics. The problem is related to the population mean. The population mean is unknown and the population variance is known. Just now we have done it in the interval estimation. Whenever you have such a problem, the test statistics is a sample mean minus mu divided by sigma by root n, that is a test statistics. So, same test statistics you can take it, fine, because the population follows a normal distribution. Therefore, each sample also follows a normal distribution. Therefore, the sample mean is also follows a normal distribution with the mean mu and the variance sigma square by n. Therefore, the test statistics is z. Actually, I missed one point. I should write z is equal to capital X bar minus mu divided by sigma by root n. That step is missing here. What I wrote small z naught, that is correct. What I wrote in the first step 2, that z, that is wrong. That is capital X bar minus mu divided by sigma divided root n, that is such a statistics that follows a standard normal distribution, fine. Now, step 3, you identify or you obtain the value using the observed information for the you find out the value of test statistics with the null hypothesis and observed information. That is step 3. Find out the value of test statistics with the help of null hypothesis and observed information. That means whatever it says in the null hypothesis, that has to be supplied. Whatever the observed information you got it from the random sample of size n, that information you have to plug in. Therefore, finally you will end up with the number. Therefore, the test statistics has to be always a function of random samples with known parameter values and the unknown parameter which is involved in the null hypothesis, nothing else. You should not have any other parameters involvement in the statistics other than the known and only one null hypothesis information, that is it. Then only it is going to be called as a test statistics. Fine. So, you get the value small z naught, and step 4 you identify where is the critical region for this test statistics. That means at what point you will have the probability alpha going to lies, or what point onwards the probability, if it is a symmetric then alpha by 2 and alpha by 2, if it is a non-symmetric then it is alpha, but we usually go for symmetric way for both standard normal distribution and the t distribution. If it is a chi-square and f, that is a non-symmetric distribution, but still we keep alpha by 2 in one side and left side we will keep the alpha by 2. Therefore, the critical region is divided into two parts. So, you identify what is the point in which the critical region starts. So, that point is identified, that is where the z naught is going to be. Whether you have to identify what is the critical region starting point. In this problem it is that is 2.57, the point in which the critical region starts in both the ends. Left side is minus 2.57, right side is 2.57. You can draw the diagram, you can draw the nicely probability density function of standard normal distribution, then you can identify the 2 points in which the probability is going to be alpha by 2 and left side is alpha by 2. So, the step 4 is identifying the critical region. You see that there is no same information is used in more than one steps. The step 1 talk about only statement, step 2 talk about only the test statistics. Here I made a mistake, it is a capital X bar minus mu divided by sigma by root. Step 3, find out the value of the test statistics with the help of observed information and with the help of null hypothesis. That is nothing to do with alpha. The step 3 is nothing to do with alpha. Step 4 is nothing to do with the sample information. It is with the test statistics identifying the critical starting point, starting point of the critical region. If it is a symmetric, then it is a 2 points and so on. So, step 4 is completely not related with the step 3. Step 4 involved only the test statistics and the alpha value. Step 3 involves step 1 test statistics and the observed information and the null hypothesis. Fine. Step 5 is a conclusion. Now, you have to see step 3 and step 4 and you have to identify where your z naught value is lies, whether within the acceptance region or rejection region or critical region. Based on that you conclude to reject or not to reject. So, always the statement is if the null hypothesis will be rejected if it is in the rejection region. Always rejection or acceptance we are talking with respect to the null hypothesis. So, we should not confuse. So, null hypothesis will be rejected if the step 3 value is lies within the critical region. Instead of using the word null hypothesis is accepted, the better statement is null hypothesis will be not to be rejected if the z naught values lies not in the critical region. Why I am saying the word is not to be rejected is better than accepted? All the conclusion is based on the random sample of size n and alpha level of significance. Therefore, whenever you get the different set of random sample of size n, obviously your conclusion is going to be changed. There is a possibility to be changed or it may not change also based on the value. Therefore, you cannot make a very strong statement of the null hypothesis is accepted. Instead of that, better, because all the conclusions are based on the state, based on the sample information. Therefore, we should use the word the null hypothesis is not to be rejected whenever the test statistics values is not in the critical region or acceptance region. We can use the word acceptance region, that is fine. Oh, sorry. So, let me repeat the word. So, the null hypothesis is not to be rejected whenever the test statistics value is lies within the acceptance region. So, with the first problem we have explained how one can do the testing of hypothesis regarding the population mean whenever the population variance is known. Now, we are coming to the situation, same statement, null hypothesis regarding the population mean, but now the population variance is unknown. The similar exercise we have done it in the interval estimation. Therefore, we will end up with the new or another test statistics, that is the t distribution. Yeah, here I have written x bar minus mu divided by s square root of n, that is a test statistics. Once you identify the test statistics, then all the steps whatever I was telling, step 2, step 3, step 4 and step 5 all are going to follow with this test statistics. That means, you identify the value, you obtain the value with the help of sample information and the null hypothesis. Then for a given alpha, you identify what is the critical region. Now, you have to identify the critical region from the t distribution. Again, the t distribution also symmetric, therefore, you can easily obtain what is the point in which the right tail probability is alpha by 2. Therefore, the critical region is divided into 2 halves, alpha by 2, and based on the T naught value, whether it is lies within the acceptance region or rejection region, accordingly you can conclude the null hypothesis will be not to be rejected or to be rejected. Fine. There is another important information. Whenever you have a sample of size n which is greater than or equal to 30, I would have said the same information in the earlier also, I forgot to tell you. So, whenever the data size is more than 30, there is no need to use the t distribution, because the t distribution with the degrees of freedom when it is going to be greater than or equal to 30, it will be approximated with the standard normal distribution. Therefore, you can use the test statistics of standard normal distribution instead of t distribution, because for n greater than or equal to 30, the t distribution will be replaced by a standard normal distribution. Now, we can extend the same exercise for the 2 independent populations also. Our interest is to find out our interest is to validate or verify the null hypothesis of difference of the population mean is going to be this much or not. So, you can create the test statistics accordingly, you can get the value, follow the same 5 steps what I said it in the first one, follow the same 5 steps, making the statement hypothesis, that is step 1, identifying the test statistics step 2, finding out the value of the test statistics with the help of sample information and the null hypothesis, that is step 3, and step 4 identify the critical region for this test statistics, that is step 4. Then you compare the step 3 result and the step 4 result, that is going to be the conclusion of the step 5. That is if Z naught falls within the critical region, then the null hypothesis is rejected. I have made it nicely in the form of table. The null hypothesis is in the first top. I have not changed the null hypothesis at every different alternate hypothesis. If I say the alternate hypothesis is mu is greater than mu naught, that means that the null hypothesis can be thought of mu less than or equal to mu naught. So, I did not write repeatedly what is a alternate hypothesis, what is a null hypothesis at every different alternate hypothesis. I have initially started with mu is equal to mu naught. Therefore, according to the alternate hypothesis, you can think of negation of that as the null hypothesis. Fine. And the important information is now whenever it is going to be less than or equal to or greater than or equal to for the null hypothesis, then the critical region is not divided into two halves. Then those tests is going to be call it as a one sided test. So, we started with a two sided test because the null hypothesis is with the equal sign. Therefore, the alternate hypothesis with the not equal to sign. Therefore, you have a critical region is divided into two halves. There is a theory behind that by using a Neyman-Pearson lemma and so on, that I have skipped it. So, based on the theory, if the null hypothesis with the equal sign, then you will have the two sided test. If the null hypothesis of less than or equal to or greater than or equal to, accordingly the critical region is going to be one side. Therefore, you conclude reject null hypothesis if so and so condition is satisfied. So, that means the step 3, step 4 is going to be same. Step 4 now it is going to be only one point in which the critical region will have a probability is going to be alpha. There is no alpha by 2. Earlier you divide alpha into two halves. Now we are keeping alpha as it is in right side or left side based on the null hypothesis. So, that you can have a look. Since it is a symmetric, that is job is easy. Then later when when sigma square is known for the two populations, I have made the table. The same exercise can be extended. Yeah. So, now I am going for when the population variance is unknown for the two independent populations. So, similar exercise, but one information which I missed it in the earlier class, even though the population variance are unknown, we should keep it which is common, then you can do these pooled sample variance. Otherwise, if you are not keeping it as same, then you will not get this calculation. So, we should they are unknown, but we have to assume that they are equal. With that calculation only you will land up the pooled sample variance. Accordingly, you will land up with the t distribution with the denominator with the s suffix p, that is a pooled sample standard deviation. Fine. The populations are unknown and you assume that they are equal, then you identified the sample variance, then you get the t distribution with the n1 plus n2 minus 2 degrees of freedom, where n1 is the sample size of the first population. From the first population you take a sample of size n1 and the second population you take a sample of size n2, fine. So, whatever I have said the theory with the simple one that can be extended the way we extended the interval estimation, the same way we can be extended. Now, we will discuss one simple example for this theory. Consider this example. The average return of a portfolio A of 10 stocks was 77%. The average return on a similar portfolio, same stocks but with the special weight balance method, let us portfolio B of 10 stocks was 75%. Carry out a statistical test to assess whether the portfolio with a special balancing method has the same return as portfolio at 5% level of significance. Instead of providing individual random sample, they have provided summation of I is equal to 1 to 10 xi square value is given. Similarly, for the other 10 stocks, summation of I is equal to 1 to 10 yi squares value is given instead of providing the actual values. Assume that the returns are assume that returns are normally distributed and that the variance of underlying distribution of each portfolio is the same. So, the question is we have to test the hypothesis. With the null hypothesis, the means population means are going to be same, and the alternate hypothesis population means are not same. Here the test statistics is a capital T, and you can follow the theory which we have just now said. We can follow the theory what we have described just now. You can use this theory and you can get the value of pooled sample variance, that is SP square, and n1 is 10 and n2 is 10. Therefore, you can find what is the table value for T of n1 plus n2 minus 2. You will get the T naught value as well as you can get the table value. Then you can compare for the T distribution of T18 with the 5%. So, I have not used here correctly. So, this notation is basically you should find out what is the table value for the T distribution with the degrees of freedom is 18 with the 5%. Then you can come to the conclusion the value of T naught that is less than 1.734, that is a table value. So, we have insufficient evidence to reject H naught at the 5% level. Therefore, it is reasonable to conclude that the portfolio with the special balancing method has the same return as that of a portfolio. So, this is a simple example to understand the theory which we have just now explained in this concept. With this, let me complete the lecture 1 of hypothesis testing. In this lecture, we have covered the idea about the testing of hypothesis and what is the definition and what are all the important jargons starting from critical region, test statistics, type 1 error, type 2 error, alpha, beta and so on that we discussed. Then we have given very simple testing of hypothesis regarding the population mean when it is a known population variance, when population variance is unknown, and also with the two independent populations also. So, with this let me complete the lecture 1. Thank you.